Hey there everyone, welcome back. We are continuing on with our lessons on work and energy, and today we are going to learn about power and efficiency. Now, power is one of these terms that in everyday language we use kind of synonymously with work or force or effort or energy, but in physics we have really specific definitions for things, and so we have to be careful what these mean. A good example of this would be if I told you that I did 1,000,000 joules of work and asked you if you were impressed. Your answer should be, well, maybe. Like, did you do 1,000,000 joules of work like in the last minute? Because that would be really impressive. But have you done 1,000,000 joules of work this entire year? That's significantly less impressive. So really, when we talk about power, we're also bringing this idea of like, well, how quickly is work happening? How quickly is energy being used? And so we say that power is the rate of doing work. And so power brings in this idea of not just how much energy was used, but also how much time passed while you were using that energy. So we can just define power really strictly as being just the work over time. And of course, because work is a change in energy, we can just think of that as a change in energy over time. And we'll see that depending on the situation, the type of energy that might be changing could be potential or kinetic or maybe even something else. It's worth pointing out that the units for work are watts. Okay, so joules per second is known as a watt, which is a W, and that's a little bit irritating because W, capital W, is also our symbol for work, but work is a variable. It's a thing we measure, whereas W for watts is a unit that's attached to the thing we measure for power. So just keep an eye out for that. Okay, so we've got an example here. A physics student, for some, I'm sure justified reason, is body slamming a biology student. He lifts the 75-kilogram student clear over his head to a height of 2.2 meters in 0.675 seconds. How much power did the physics student generate? So power, as we said, is work over time, which we know is really just a change in energy over time. Now, if you're lifting somebody up over your head, the energy that's changing, in that case, the work that's being done would be a change in potential energy because you're lifting something up against gravity. So in this case, this would just equal mgh divided by t. And so when we sub in our values here, 75 times 9.8 times a height of 2.2, that's pretty high up. I hope they're okay. Divided by 0.675. Crunching this into your calculator, you should find that you get about 2,400 watts, 2,400 watts. Okay, so another example here. While cruising along level ground in a one-horse open sleigh at 4 meters per second, Mr. Trask cracks the whip and speeds up to 12 meters per second in 4.5 seconds. So the sleigh has a mass of 850 kilograms. How much power did it generate? Did the horse, I guess, generate in this case? And note that we're going to ignore friction. So power, as we know, is a change in energy over time. But if I'm just going over level ground and accelerating, then the work that's being done is changing the kinetic energy of the car, not the potential energy. So in this case, it's a change, just a change in kinetic. Now, I just want to point out that this is going to be equal to 1/2 m delta v squared, all divided by time. And we have to be a little bit careful about the delta v squared, because this needs to be 1/2 m v final squared minus v initial squared divided by time. We need to square the velocities and then, or the speeds, and then subtract them, as opposed to subtracting them and then squaring them. We end up with a very different answer if we do that. And so plugging in all my values, I get 1/2 times the mass, which is 850, times 12 squared minus 4 squared, all divided by 4.5 seconds, and we end up with a total power of about 12,000 watts. Good for that horse. Okay. Another useful equation that we might use when it comes to power is if we have an object that's moving at a constant velocity, we could say that power is equal to work over time. Now you remember that work is also defined as force times displacement. So force times displacement over time. And this thing right here, d over t, that should be familiar to you because you remember, I'm sure, that we define velocity as displacement over time. So these are the same thing, which means I can just substitute in V into this space here for d over t, and what I end up with is just power equals force times velocity. Now, it's important to note that this will only work at a constant velocity. Only at a constant velocity. And why is that? Well, that's because this formula here, V equals d over t, that formula only really works at a constant velocity. So, so does the formula P equals FV. An example of that would be a student pushing their physics homework, 14 kilograms of physics homework, so quite a bit, up a ramp, and they're pushing it at a constant velocity. So I've got a force of gravity pulling down, and then I've got like this applied force up the ramp, and they're pushing it at a constant velocity. So, so my net force must be 0. I've got a normal force here, and then I guess I've also got a force of friction also pulling down the ramp there. So it's getting a little bit busy, but that's kind of the setup. Now, just like we learned last unit, when we deal with inclines, we can break our force of gravity into perpendicular and parallel components. So I've got an FG parallel here, and just note that this is 40 degrees, which means that this is 40 degrees. And so that's a lot, but the point being that the power is just going to be the force used to move up the ramp times the velocity. And so it's just going to be the applied force times the velocity. Now, the applied force, because the net force is 0, because there's because the velocity is constant and therefore no acceleration, the net force is 0, which means my applied force would just be equal to the parallel component of gravity plus the force of friction. And so that's going to equal mg sine 40 plus the force of friction, which if I sub in all my values, I get 14 times 9.8 times the sine of 40 plus 26, and it's getting pretty squishy there. I'm going to end up with about 114 newtons, and so I can bring that over to my power equation and solve here for the power. 114 times 3.2 gives me a total power output of about 365 watts. Okay, so that's the idea of power, and it's, again, if you're comfortable with energy and work, then power is just a little extension of that. It's not too tricky. Just the big thing to recognize is that power is going to depend on time, whereas work doesn't. One of the things that makes power really useful is it helps us understand how machines work, right? Because it doesn't do you any good to know that, oh, hey, this car can do 1 billion joules of work if it's going to take 10 years to do that work. So we often refer to the power output of a vehicle or of an appliance or some sort of tool, so we get an idea of like how much work it can do, how quickly. Now, the other thing that becomes really important with machines whenever we use them is the idea of efficiency. So whenever you put energy into a machine to do a job, whether it's you push down on the gas pedal of your car or you push down on the toaster to toast your toast, the energy that goes into the machine doesn't get completely turned into useful energy. And useful work is not always done. Some gets wasted, and it gets wasted in any number of ways. But one of the main ways that we see with like mechanical things is that the work is going to get wasted by friction, which is generally going to just turn into thermal energy. It's going to flow as heat out of the system. So whenever we have things like, for example, different machines are going to have a different efficiency. And so, like, for example, an electric heater is like 99% efficient, which is like fantastic because all the energy you put into electricity is basically going to turn into heat, which is what you wanted in the first place. Whereas a car, like a gasoline car, might only be like about 30% efficient. That means that all of the chemical energy stored in the gasoline, when it goes into the engine and it is exploded and turned into heat and turns the piston or cranks the pistons, which turns the wheels, there's a whole bunch of wasted energy in that process, and only about 30% of what could be used to move the car actually is turned into useful work. And then another example would be a light bulb, and I'm thinking of like an old school incandescent light bulb. Those things are probably like around 2% efficient or something like that. If you have a light bulb, it's actually pretty terrible at turning energy to light. It's actually very good at turning energy into heat, because if you've ever gone to try and change a light bulb after it's burnt out, you realize that those things are generating a ton of heat. I mean, even modern light bulbs that are much more efficient might be 15 or 20% efficient, or even 30% efficient. There's still a lot of wasted energy there. So we can kind of define efficiency in two ways. We say that the efficiency of a machine is the work out divided by the work in times 100%. So the work that it comes out of the machine divided by the work that you actually put in times 100% to make it a percentage. Or we can do the same thing with power. So we can say the power out divided by the power in times 100%. Pout over pin. So how much power did the machine actually use for you usefully versus how much power did you have to supply to it so that it actually did its job. And you note that these are ratios. It's a ratio of energy to energy or power to power, and so there are no units. It's sometimes a little bit tricky to figure out what we mean by power out or work out, and that's usually the hardest part of kind of figuring out these problems. The first thing to recognize is, so the power in is the energy that was supplied to the machine, the energy you have to give to the machine in order for it to do its job. So the energy or the power supplied to the machine. Okay, like if you think of a really simple example of like a lever, well, the energy you have to put in is you physically have to exert a force on one end of the lever to push down. So the energy that you put into that machine versus the energy or the power out is, in my mind, it's just what does it actually do? So what the machine actually does. Okay, so if you're talking about a lever again, I had to exert a force on this end here. I had to push down on this end to make the machine work, and then over on this other end, it lifted a thing. So here's my input, and over there is my output, and it's going to typically work like that. So while it can be kind of tricky to just off the top of your head look at a problem and know which one is power input and which one's power output, one thing to keep in mind is that because of thermodynamics, energy is always lost in this process. Anytime you use energy to do anything, you're always going to have some waste. So what that means is the work that you put in is always going to be greater than the work that you get out. And therefore, the efficiency is always going to be less than 100%. You certainly can't get more than 100% efficient, because that would break the law of conservation of energy, but the reality is you can't actually even be 100% efficient. No real world machine can even get you to 100% because there's always going to be some waste. So a couple of ways to think about this, and again, this whole like efficiency idea is going to work on simple machines or very complicated machines. So an example of a much more complicated machine would be the Top Thrill Dragster. If any of you are roller coaster fans, you might know it is one of the tallest roller coasters in the entire world, and essentially a car is just accelerated along a track, and then it turns 90 degrees and goes straight up in the air. And just to get a sense of just how crazy this is, here's like a quick video clip that gives you an idea of this. The car is basically just accelerated forwards over a pretty short distance, well, a couple 100 meters or so, and then it turns 90 degrees, goes up in the air, and just barely makes it over the top before falling back down the other side. And when they get it just right, the car has just enough energy to just barely get to the top. The key to recognize with this is that the whole energy input for this machine happens right now during the acceleration phase. So it's launched forward by a cable, and then after it turns, now it has to make it up over the hill all under its own power. There's no more power supplied to it. And again, when we do it just right, it just barely makes it over the hill, so that it's that extra bit of thrilling. So we can draw a, maybe not quite as detailed, but a rough picture here that basically this is the whole idea. So the Top Thrill Dragster cart starts here and then starts at rest, right? It's not moving. And by the time it gets to this point here, it has to be going like crazy fast. It has to go so fast that it can just barely make it over the top of the roller coaster before it goes down the other side. Okay, so let's see what they want to know. They want to, first of all, find the minimum amount of work required, done on the car in order for it to reach its peak. So if this was like a perfectly frictionless situation and there was no wasted energy and we're not worried about any of that, what's like the minimum work required just to barely get it over the top of that peak? Well, I guess the work needed in this case is going to be the change in energy, which would be the potential energy. It needs to start at the bottom and it needs to have enough energy to get 120 meters in the air. So that's just going to be mgh. And notice that if you just barely get at the top, then all of the kinetic energy at the bottom is entirely converted into potential at the top. So we don't have any leftover kinetic to worry about. So this is going to equal the mass of the cart, which is 2,800 kilograms times 9.8 times 120 meters, which is just actually insane just to say out loud how high this thing is. The total work here is it's 3,290,000 joules, which is crazy. You could write that as like about 3.3 times 10 to the 6 joules if you wanted to. So you have to do a 3 million joules of work to get this thing up and over the hill. But of course, that's not going to do it. If you only gave it 3.3 million joules of energy, it wouldn't make it to the top because there's air resistance and there's friction in the track and all sorts of wasted forms of energy, heat and whatever else. And so in reality, what has to happen is the roller coaster has to go from 0 to 193 kilometers per hour in 3.8 seconds during that like acceleration phase. So the actual speed it needs to reach is 193 kilometers an hour. Okay, so the work that like you actually have to do, and I'm going to split this up into work and power, because I know it's coming later. So the work that I actually have to do on the car really is to change its kinetic energy. And so I have a changing kinetic energy, which would be 1/2 m delta v squared. Now recognize that the initial velocity is 0, so really this is just 1/2 v final squared. So 1/2 mv final squared. I did notice here that I've got my speed here in kilometers per hour, so can't forget to divide that by 3.6. So I'm just going to divide that by 3.6 and make a note that that's something like 53.61 meters per second, because I can't use that kilometer per hour number. So the work done here is just going to equal, let's see, plug in my values. I've got 1/2 times the mass of the car, which is 2,800 kilograms, times 53.61 meters per second squared. And so it turns out that I actually have to input over 4 million joules. It's 4,023,000 joules of work. You can see right away the difference, right? I had to put in a little bit more than the minimum or this isn't going to work. So in terms of the power output, well, the power is just the work over time. So my 4.04023,000 divided by the time, which is 3.8 seconds, gets me a total power of 1.05 times 10 to the 6 watts, which is just over a megawatt. So quite a bit of power needed to make this machine run. Now the last question here on this side is to find the efficiency. So for the efficiency, I can talk about power or I can talk about work. But since I already know the work, minimum work and total work, I'm going to use those. So I'm going to say efficiency is just work output over work input times 100%. Now, which is which? You can see here that the first thing I calculated was what was like the minimum work needed. Like what did the machine actually do? The roller coaster just barely made it over the hill. That's what actually happened. So that's my work output. This 3,290,000 joules is my work output. And what did I have to put in? Well, I had to put in 4,023,000 joules for it to work, and I'll multiply it by 100% just to get a percentage. So this whole thing ends up being right around about 82% efficient, which, I don't know, actually kind of sounds maybe a little bit high. I feel like this machine maybe wouldn't be quite that efficient, but who knows? Okay, another example of this would be the Incredible Hulk roller coaster, which is equally thrilling, but works a little bit differently. So this roller coaster works by launching you up a hill. So an example of this one here looks like this. You start off in a tunnel, and then the whole cart gets launched forward from basically rest to like some crazy speed before you come flying out the tunnel. Now, not only are you being launched forwards, but you're also being launched upwards. You actually go up a ramp through this whole process, and then of course you have to have enough speed to go through and do the whole rest of the ride. And I definitely recommend you check that out some other time. So that's going to be a little bit different. In this case, what I've got is I've got a ride that launches you up a ramp. Okay, so I've got this car, and there's my roller coaster car, and we're going to say it basically starts at rest. Okay, but by the time it gets to the top of the ramp, it needs to go from basically not moving to a final velocity of 64 kilometers per hour. And that ends up being that's about 17.78 meters per second. Okay, so again, I'm going to find the work first in this case. We know that work is a change in energy, but this one's a little bit different because not only is this car accelerating, but it's also going up a hill. And that means because it's accelerating, it's gaining kinetic energy, and because it's climbing a hill, it's gaining potential. So the total work done is actually the change in kinetic energy plus the change in potential energy, which means I've got 1/2 m delta v squared plus mgh. Now I'm going to assume that the initial velocity was 0. You saw in the video it wasn't quite 0, but it was pretty close to that. So we're going to fib. So I've got 1/2 times 4,500 times my final velocity, which was 17.78 squared, plus 4,500 times 9.8 times 34. And again, this is a lot of energy. This is like 2,210,000 joules. It takes a lot of energy to launch this thing up the ramp. Now, since it was asking for power, I can just say power is work over time. So 2,210,000 divided by 2 is going to be right around 1.1 times 10 to the 6 watts, or 1.1 megawatts. Now, that's what it accomplished. The ride went from rest to some speed and up a hill, and so that's the actual power output of the ride. But it turns out that when you plug this machine in, you actually have to supply it with 1.45 megawatts of energy. So to find the efficiency of the ride, we need to consider that. So the efficiency of the ride is going to be the power output divided by the power input times 100%. And you can probably tell which one's which just by looking at the numbers and seeing which one's bigger, but also just consider that, well, when you plug in a machine and it draws 1.45 megawatts, that is clearly the power you're putting into the machine, not what the machine actually does. It tells you nothing about the result. So I've got 1.1 times 10 to the 6 watts over 1.45 times 10 to the 6 watts times 100%, and so this ends up being right around 76% efficient. Cool. So the last question here is saying, okay, so now the car goes through its whole, like, over the loops and over the hills and so on, and then when the ride is finally done, it pulls back into the station, the same station it left with, and it pulls back into the station, and it's still moving at 8 meters per second. How much heat has been generated through this whole process, or like dispersed into the surroundings? How much thermal energy has been generated, I should say? Well, it should make sense that the total energy that you start with is going to equal the total energy you end up with, like mechanical energy, I should say, plus whatever amount of heat has flown out of the system. So the mechanical energy, the difference in mechanical energy should be my heat. So the heat that left the system would be the initial energy minus the final energy that I ended up with. Now the final energy, I can calculate that because the final energy that the car has is all kinetic. So it's 1/2 mv squared, which is 1/2 times 4,500 times, I'm moving at 8 meters per second. So you can see I've lost most of my energy. In fact, it's only got about 144,000 joules left when it pulls into the station. And so the energy that was turned into heat is going to be the difference between what I started with. And I found that back up here. I started with over 2 million joules. So I started with 2,210,000 joules, and I only ended up with 144,000 joules. And so what that means is, in terms of wasted energy, it's like 2.07 times 10 to the 6, so 2 million joules was transformed into thermal energy. Okay, that is it for power and efficiency.